Alrighty, so this is Unit 6, Learning Objective 9. This is learning objective states that we need to explain and relate Avogadro's hypothesis to the molar volume of a gas at standard temperature pressure. Avogadro's law, or hypothesis, whatever you want to call it, is really a law now. So it's not really hypothesis anymore. It was his hypothesis at first, and now it's his law. It states that equal volumes of gases at the same temperature and pressure contain equal numbers of particles, which we now know to be moles. So equal volumes of gases at the same temperature and pressure contain equal numbers of moles. The volume occupied by 1 mole of a gas at STP, this is standard temperature pressure, is known as molar volume. Standard temperature is 0 degrees Celsius and standard pressure is 1 atm. So I like to say that STP goes from 0 to 1, 0 Celsius, 1 atmosphere. The equality here that we use is 1 mole of a gas is equal to 22.4 liters of a gas. Now that gas has to be at STP. We can't use that at any other value for temperature, pressure. It has to be at STP. So, but why is that? Why is it 22.4? Where does that 22.4 number come from? Well, let's see that. So what is the volume of 1 mole of hydrogen gas at standard temperature pressure? So let's plug this into our equation, PIV-NERD. So PV equals nRT. We're going to solve for volume here. So we're going to divide everything by P. So volume is equal to nRT over P. Well, if I'm at standard temperature, I'm at 273 Kelvin. And if I'm at standard pressure, I'm at 1 atmosphere. So the reason it's 273 is 0 plus 273 is equal to 273 Kelvin. So if I've got 1 mole times my R value, which is 0.0821, this is atmospheres times liters, all over mole times Kelvin. And then temperature is 273 Kelvin. Kelvin's canceling out. And then moles are also canceling out. And then I have pressure, which is 1 atm, which is canceling there. And I'm in liters. So let's see what this gives me. So 0.0821 times 273. So that's all I have to multiply there. It's equal to 22.4133 liters. There's your 22.4. Let's look at an example here. It says a chemical reaction produces 0.678 moles of hydrogen gas. It says what is the total volume in liters that is occupied at this gas at STP. Now we want to make sure that it says STP before we use the 22.4. If it's not at STP, we cannot use the 22.4. So let's see this. So I need to go from moles to volume to liters. So I'm going to go back to my roadmap here. So this is the stoichiometry roadmap, which we did in Unit 4. And I want to add on to this roadmap. Now, if you were in my class, you already have this, but we have particles here, and we go through the 6.02 times 10 to the 23rd. And again, if you're going up, you're going to multiply. If you're going into the bowl, you're going to divide. And then the same thing's over here. So you get particles at the top here, which again, you're going through the 6.02 times 10 to the 23rd. Now, you have one other area here. I'm going to kind of erase this here. You should know that when you go through your mole ratio, it's coming from your balanced chemical equation coefficients. But you also had off of here volume. And this was a gas. This was at STP. Same thing here. So you had volume of a gas. At STP. And again, the number that goes here is the 22.4 liters. So 22.4 liters. So we've been adding on to this roadmap since unit 3, really, because our actual initial roadmap was just one side of this right here. So that was in the mole unit. And then we added the second side to this for your stoichiometry unit. So we're adding on the volume of a gas at STP for unit 6 here. Now, there is a road between volume of a gas to volume of gas. So it kind of makes this block. It's the mole ratio. So how kind of similar to how we have names of roads that have multiple of the same name. This guy's mole ratio from moles of substance A to moles of substance B. And then this is also going to be the mole ratio from moles of substance A to moles of substance B. And it's still the same. It's moles of substance B over moles of substance A. So that is your roadmap for this guy. So then, if we're going from moles to liters, again, remember, anytime you're going out of the mole, so like when you go from mole of something to a different unit, you are multiplying. And whenever you're going from into the mole, you're dividing. So out of the mole, multiply, into the mole, divide. So my setup for this, I start with what I'm given. I'm given 0.687 moles of H2. I know that for 1 mole of H2 at standard temperature pressure, I have 22.4 liters of H2. So moles of H2 are canceling out. And then I can calculate that. So for that, I'm going to do 0.687 times 22.4. That gives me 15.4 liters of H2. And that is my answer for that one. Let's look at another example just to kind of give you a little bit of a better grasp on this, maybe. So it says a reaction produced 0.789 grams of oxygen gas. It's asking how many liters of oxygen gas do you have at standard temperature pressure? All right, go back to my roadmap. If I'm in mass of oxygen, I need to get into volume of oxygen. So I go through my atomic mass of oxygen into my mole of oxygen, and then I can go through my volume of oxygen. So oxygen is magnificent. He's absolutely magnificent. So 0.789 grams of O2. Reason he's magnificent is because he's got 2. My first step is going through the molar mass. So 32.00 grams of oxygen over 1 mole of oxygen. And then again, another, because we've gone through two roads, right? So we've gone through 2 roads. 1 is the atomic mass. 2 is going to be the 22.4 liters. Again, if we go into divide, out of multiply. So then here we have 1 mole of O2 and 22.4 liters of O2. So moles of O2 are canceling, grams of O2 are canceling, and we are in liters of oxygen. So then to plug this into our calculator here, we're going to do 0.789 divided by 32 times 22.4. And that gives me 0.5523. Always round to 3, so always round to your proper number of sig figs. That always comes from the given number here. So I've got 3 sig figs here. That means I need 3 sig figs in my answer. So 0.552 liters of oxygen gas. And that's my answer, and I'm done. Woohoo!